In this module, we will consider the Doppler effect. Waves travel through the air at some given speed that depends on the temperature and pressure of the air, but not on the motion of the source through the air. In other words, if you create a pressure enhancement in the air, it will travel from its point of creation at the speed of sound as measured with respect to the rest frame of the air. If there is relative motion between the source of and the observer of some sound waves, the frequency of the observed sound waves will be different from their frequency as emitted by the source. In the following examples, we will consider a source of sound emitting sinusoidal waves. We will keep track of individual pressure maxima, each of which we will call a pulse. The source will emit a new pulse at intervals equal to the period Ts of the waves being emitted. The observer will record the arrival time of these pulses, and the interval of time, T0, between successive pulses is the observed period of the same waves. Consider the example where the observer is at rest and the source of the sound is moving toward the observer. At t equals 0, the source emits a pulse that travels toward the observer. It travels a distance d during the time interval t sub s until the next pulse leaves the source. This distance is the speed of the wave times the wave period t sub s. Also, during the same time interval, the source moves toward the observer by a distance d sub s equal to the speed of the source times the wave period t sub s. The next pulse, in order to reach the same position in space the previous pulse had when the new pulse was emitted, must travel a distance do equal to the speed of the sound waves times to. This time interval to will be the period of the waves as measured by the stationary observer. Replacing the distances d and d sub s, and replacing the wave periods with the wave frequencies, we arrive at a relationship between the source and observer frequencies. Similarly, if the source is stationary, but the observer is moving toward the source, we can begin by defining a distance d between successive pulses from the source and choose time t equals 0 as the moment the leading pulse arrives at the observer. The distance d is again equal to the speed of the wave times the wave period t sub s. After a time to, the observer will have moved toward the source to the point where it meets the next pulse. It travels a distance do equal to the observer's speed times the time interval to. This time interval is the period of the waves as measured by the observer. During the same time interval, the second pulse traveled a distance ds equal to the wave speed times to. Replacing the distances d and do, and replacing the wave periods with wave frequencies, we again arrive at a relationship between the source and observer frequencies. It is important to remember that the speeds v, vs, and vo occurring in the previous equations are all positive numbers and are measured with respect to the rest frame of the air in which the sound is traveling. The frequency fs is measured in the rest frame of the source of the sound, and the frequency fo is measured in the rest frame of the observer. If the source or observer is moving away from the other, then the signs in the corresponding equations change. For the case when only the source is moving, the difference between the two speeds in the denominator indicates that the source is moving toward the observer. If we change the minus sign to a plus sign, this indicates that the source is moving away from the observer. If we consider the case where only the observer is moving, then the sum of the speeds in the numerator indicates that the observer is moving toward the source. If we change the plus sign to a minus sign, then the observer is moving away from the source. Note that in both cases, if the moving component is moving toward the stationary component, as measured in the rest frame of the air, the frequency increases. If it is moving away, then the frequency decreases. If the observer is stationary with respect to the air, then FO is equal to FA, the frequency of the waves in the rest frame of the air. Similarly, if it is the source which is stationary, then it is Fs which is equal to the frequency of the waves in the rest frame of the air. Using this, we can combine the equations for moving source and moving observer. We start with the equation for the observer alone moving, in which case it is Fs, which is the frequency of the waves in the rest frame of the air. We then replace this with the source moving equation, and we wind up with an equation which describes both the source and observer as moving. If both the source and observer are moving, we must be clear about how the signs work. The observer moving toward the source does not mean that the distance between the source and observer must be decreasing. If the source is moving away from the observer at a speed faster than the observer is moving toward the source, then the distance between them will be increasing. Even though the sign choices are related to motion relative to the rest frame of the air, the ultimate result of the Doppler effect depends on the relative motion of the source and observer. For example, if the source is moving toward the observer at the same speed with which the observer is moving away from the source, then the signs of the terms in the numerator and denominator of the equation will be equal and the terms will cancel. In that case, the observed frequency and the source frequency will be the same, and there is no Doppler shift.